So hopefully you guys enjoyed your Monday. I also heard that Tuesday you guys had like was this Tuesday? It was like a day, mental health day for the school. Okay, that's good. That's good. So let's get started. A couple of reminders. All right, so announcements. We have a lot of stuff to cover today. So hopefully everybody watched lecture 26. Let's Jonathan and Isaiah, let's get started. You guys, you're good. So reminder, there is a Hack NCAT 5.0 remix is a hackathon going on. I will give bonus points for people that attend at least one of these 2 days. Okay, so please go. It'll be helpful at the minimum. You don't even like, sometimes hackathons are not even so much for the stuff you build, but it's the people you meet, the cool stuff you see. And then also it's just a good chance to chat with folks from, Google, Amazon, Salesforce. I checked, Meta's not going to be there. I don't know why. It's just how it is. But if you signed up for the mock interview, then those will also be happening. I think April-ish, the first week of April. So it's April 1st. Who's already signed up for this? Who's definitely going? Oh, great. That's perfect. All right. It's kind of funny because if everybody gets bonus points, then but anyway. All right, homework 7, I changed the due date for this, many reasons. One reason is because you shouldn't have been working on Tuesday, I guess. Technically, that was a mental health day, so hopefully you guys took that day off and just enjoyed it. The other reason is I'm falling behind on coming up with your homework assignments, so I have not gotten into homework 8 because there's been a lot of stuff to do. So I am giving myself a few extra days, and I'm giving you guys a few extra days. So this homework 7 is actually not going to be due until Friday at 11:59 p.m. Okay. Grade scope is updated. Yeah.
So when will homework 8 be released?
Probably on Friday. I will try to aim for that. Yeah, I will try to aim for even earlier than that if I can. But it's just I am running and trying to keep up, and I just realized that if I don't work on the weekends, it turns out I can't do all the stuff that I want to do. So yeah.
Is there gonna be a homework party today?
Yeah, you can come. You guys can come back with me. So it's if anybody wants to come. Anytime after lecture, I think I'm just going to be hanging out in the Martin building now. So if anybody wants to show up anytime there, I'm usually there till like 5 or something, most days, Monday, Wednesday, Friday after lecture. And I'm always happy to try to chat with you guys. I have to hop on a call at 2 because we are recruiting more EIRs for next semester at Meta. And they want to ask questions about what it's like. So I may either join the call from the little room that we have, or I will drop off and join. But yeah, if you guys want to come, feel free. I can try to help you with anything with homework 7. But it is going to be due Friday. I'll probably have another homework party on Friday as well, just right after class. Yeah. And homework 7 walkthrough. I did get around to finally recording this. It's uploaded. I think I uploaded it yesterday. It goes through both the written and the coding portion. So one thing to keep in mind for the coding portion is that everybody has different graphs, okay? It depends. And then another thing to keep in mind is after I released the homework, I realized that the random number generator that we were using is not consistent across machines. So it was giving a different graph for the same seed in Gradescope versus what you saw in Replit. So I had to go in and change it. So if you are one of those people that got started early, I'm sorry, but you were likely punished. Because your graph probably changed after I changed the random number generator. So you will have to redo some of the work. So I'm really sorry about that, but it has to be done so that the auto grader works. Yeah. All right. Yeah. So like I said, so homework party, come with me after class if you have time, 1 to 2 p.m. I'll be there answering questions. I have a meeting 2 to 2:30, and then I'll stick around afterwards if you have more questions. All right. That's it for announcements, I think. Does anybody else have any announcements they want to share? Any new progress on business ventures that you guys are running? I thought we had a couple of entrepreneurs in the class, but. Oh, Jonathan, you have an announcement? Yeah.
I know it's going to be during the hackathon, but my fraternity puts on an American music recital every year.
Oh.
And it's going to be on Friday in the Student Center from 6 to 7.
All right. So a music recital, 6 to 7 on Friday. If you guys are into that, you can attend. Cool. All right. other than that, let's jump right into lecture. So we are going to be, this is the last lecture, I hope, that we're going to do on dynamic programming. So if you guys have noticed, we have done technically Bellman-Ford, Floyd-Warshall, least common subsequence. And if you watched lecture 26, we also did Knapsack Unbounded, all of which are dynamic programming problems. Okay, so if you missed lecture 26, you're probably going to be fine. A lot of our lectures are not necessarily building on top of each other, but I do encourage you to watch lecture 26 from Monday. Okay, and the video's up. Oh, that's the other thing. I guess I won't do it. I don't know if you guys noticed, but I was trying this thing where I have an iPad and I can annotate on the slides while I was presenting. I'll try that for Friday when I have more time. All right, so from last lecture, if you guys remember, it turns out we can actually solve the unbounded knapsack problem in time NW. Who remembers what the knapsack problem is from lecture 26? Yeah.
It was like how many of like certain items that have values and weights that fit inside the knapsack itself.
Yeah, that's exactly it. So the problem is you have a backpack. Okay. I can only carry 20 pounds, let's say, because I'm pretty weak. You know, that's the max. But you could imagine the military probably does this. What's the maximum weight that a typical soldier carries? 120 pounds, maybe? Yeah. So you can imagine, so the knapsack problem is you've got a backpack, you know, I can fit at most 10, I can carry at most 10 pounds. I can't carry more, but you can imagine, you know, this iPad weighs like, you know, half a pound and it's worth, you know, like $1,000, right? So I probably want to make sure I carry this. And this water, you know, doesn't weigh that much. It's probably, you know, worth like $1. And then, you know, you've got other random stuff in here. It's a voltmeter. You guys don't need to know why I have that, but I have that. And the problem is you have your backpack, it only fits so much weight, and each item has a certain weight to it and also a value, right? Which can be a dollar amount, right? And the goal is like, well, given that much space, that much weight I can carry, what is the set of items I can put in here that gives me the maximum value? So I make my backpack as valuable as possible, but it's still under the weight, right? So that's the knapsack problem, right? And the unbounded version of this is I have infinite copies of iPads, right? So I can take as many as I want because I'm just, there's like an infinite pool, you know, I know Bill Gates, I just set him up, he just gives me iPads, right? And that problem in lecture 26, we solved it in N times W time, where W is the maximum weight of the backpack and N is the number of items you're considering. Okay. This actually required so it was dynamic programming. That's how we solved it. It required a one-dimensional table. And we essentially what we did is we said, well, the most natural sub-problem for that problem is to consider smaller backpacks, right? Because in a way, one way to think about it is like, if this backpack can fit 10 pounds, first I can figure out, let's say I had a smaller backpack that can only fit 5 pounds. If I can figure out the optimal way to put stuff into that backpack, then really, in a sense, I can just put that backpack inside this backpack, right? So the optimal solution for smaller backpacks is the optimal solution for bigger ones, okay? Or like it helps you build the optimal solution for bigger ones, okay? So that was this. That was the unbounded knapsack. In today's lecture, we're actually going to do something that you guys probably think is a little bit more useful, right? So both of these algorithms are very useful. They're used everywhere. You can imagine they're resource optimization problems. You have a bunch of resources that cost you a certain amount, but give you a certain value, and you can only fit at most, you know, this many costs, right? So businesses, backpacks, airline budgets, like anytime you have a budget, all of that is like basically versions of knapsack, okay? And in one case, you have infinite copies, but in the case we're going to cover today is where we can actually only take one copy. So once we take an item, we can no longer take another version of that item. We only have one iPad, right? I no longer have Bill Gates' phone number. I can't hit him up to get me more iPads. All right, does that make sense for the 0, 1? So that's the problem we're trying to solve. So we're going to try to figure out an algorithm to give us what is the maximum weight. And something you guys should notice about dynamic programming is that a lot of times we solve the problem to give us a number, to be like, what is the maximum weight that we can put in here? What's the maximum value, right? And then a lot of times what you can do is you can slightly modify the algorithm to actually keep track of the things you're putting, right? Cool. All right, so again, this is the recipe for dynamic programming. So anytime you think you have a dynamic programming problem, you want to go through these 5 steps. Most of this class is spent on steps 1 through 3. So the very first step is we want to identify optimal substructure. Okay. So who wants to throw out some questions for what our sub-problems, our smaller problems might be for this new version of the knapsack problem? And I will say, I think this is like the hard part where, or like, I don't necessarily expect you guys to know. This is the part where in real life, what you do is you think of something, you try it, it doesn't work. You think something else, you try it, it doesn't work. You think something else, you try it, it doesn't work. Yeah. Yeah, so intuitive, let's say one thing you guys should think about is like, well, this doesn't seem that different from the problem we solved earlier. So maybe one sub problem is like, hey, maybe you can just try getting to smaller backpacks, right? That actually doesn't work, but that is one suggestion. Like, let's just try the same sub problem that we tried last time. Why doesn't this work? Why is this problem different where like this suggestion wouldn't work? Yeah.
When you have the larger object, it's more valuable than the smaller backpack.
So in that case, you actually just wouldn't put it in. And that's the same thing that we did last time. But there's something different. You know, so the first problem we solved was I could have as many copies of any of the items I wanted. And this problem is like once I put an iPad in, I can no longer put an iPad in. So why does making just like saying like, you know, what's the most I can fit in 10 pounds? Why does that not help me figure out what's the most I can fit in 20 pounds? What am I missing? Yeah, the limit on your items, right? So like this 10 pounds, like we need to know which items were already used because those items we cannot use when we keep adding to get to the 20 pounds, right? So in a sense, this problem is harder because you actually need to know which items you've already used, right? So yeah, this one actually doesn't work. Again, because like you guys said, we're only allowed to keep 1 copy of each item. And the subproblem needs to know what items were used and what haven't, right? So, you know, maybe I solved this problem, but I used my turtle, right? So somehow this bigger problem needs to know I can't use turtles anymore, even though maybe it's good to use a turtle, but I can't, right? I guess I should have asked you guys this question, but another suggestion you might try is you might say, hey, well, I need to know how many items I've been using. So maybe a sub problem is instead of making the backpack smaller, I say, hey, what is the optimal solution if I can only use 1 item? What is the optimal solution if I can use the first 2 items? What if I can only use the first 3, right? So that's another way to make the problem smaller. Again, it turns out that doesn't work, but that's another thing that you might think of, right? Like this is like the part where you are trying to think of ideas and then you figure out, do they work, do they not work, right? So the idea here would be, hey, my smaller problems could be like, you know, I've got tacos, fire trucks, and turtles. You know, a smaller sub problem is like, hey, maybe I don't have any fire trucks. Maybe I can only use a turtle, or sorry, I don't have any tacos, only a turtle and a fire truck. And then a smaller problem is like, hey, I don't even have turtles. Like I only have a fire truck, right? So that's trying to make the problem smaller. But if you do just this, it turns out not to work. Does somebody have any suggestions or like ideas maybe why only doing this part? So let me go back. Only doing this won't work. So again, the reason the previous one didn't work is because the backpack needed to know which items. Why does this not work? Yeah. Yeah, so the idea here is this one doesn't work because you do actually need to make the backpack smaller, right? So the problem of like, what is the maximal value I can get if I know the answer to this? Let's say what's the maximum value I can get given a weight limit of 100, and I can only use fire trucks, it actually turns out it is not very useful, or like it takes a lot of work to figure out how to then solve the problem. Hey, now I can use turtles. Okay, so it's not that it doesn't help you solve the problem. It's that when you actually try to solve it, you figure out, oh, this is actually like a lot of for loops, and it's going to be a lot of work to do, which is usually not your optimal solution. But what you do is you do both, it turns out. So you have subproblems that are both making the set of items you're considering smaller and making the backpack smaller. So now you're actually going to have a 2D matrix. So you're going to have a lot of subproblems. Okay. Does that make sense? What the smaller subproblems we're going for here is, right? So originally we want to solve, I have a certain set of items with certain weight, certain value, and I have a backpack with a maximum capacity. I want to put, what are the items I should take to give me the most value, right? That's the original question. And what we're saying is, well, really what we need to solve is we need to solve more problems in order to solve that one. The problems we're going to solve are indexed by X and A. Okay, so again, it's a two-dimensional table. So now we're going to have two variables that are going to index into the table, because now we're going to have let's say I have n items and my weight is 10. I'm going to have 10 n problems because I have to fill in this whole matrix. Okay, and the idea is, the question I'm going to ask now is, how many of the first j items? So I'm going to order my items in some order. Doesn't matter how you order them. You're just going to give them a number like 0, 1, 2, 3, right? So I'm going to say this iPad is item 1. This water is item 0, item 1, item 2, right? And the questions I'm going to be asking is, given the first j items, what is the optimal, what is the maximum value I can get if my backpack can only fit X weight? Okay, so now we're parameterizing by two variables. So we get a lot of them, right? So again, our original problem is given the first n items, so given all of the items, right? So n is like a number like 20, right? Given all the items, capacity W, like big W, which is like 100. So the big W and the n are given to you. And now we're going to create a bunch of smaller problems where we're going to solve all of them. So X is going to go, from 0 to 1 to 2 to 3 to 4, all the way up to W. And J is going to go from 0 to 1 to 2, all the way up to N. Does that make sense? Cool. So this is the optimal solution for a knapsack of size X using only the first J items. So it turns out this is a good subproblem. And the reason it's good is because you can solve it using solutions to smaller versions of itself. Okay, and we're going to talk about that. So step 2 is, once you have a good subproblem, a candidate for a subproblem, you want to write it in terms of smaller subproblems, right? Because the whole idea is we're going to be able, like, you guys should already see, like, if J is 0, what is the answer? If I can take no items, what is the maximum value any of my backpacks can have? 0. Right? If X is 0, if my backpack cannot fit any items, then what is the maximum value I can have? 0. So you know that for the base case, the easy problems, you have an answer, right? So now the question is, well, can I use the answer to those smaller problems to solve for slightly bigger problems, right? So there are actually two cases to consider here. So again, we're trying to solve. So right now we're going to think about it extrapolating. We're trying to solve the X and J case, right? XJ. We're just looking at some step in the algorithm. So the first case we're going to consider is item J. So let's say item J is our turtle, whatever it is, right? It happens to be a turtle in this case. Case 1 is that the optimal solution that can use J items, right? So this is, we can use all J items, does not use the turtle. That's one case. What's the other case? It does use it, okay? So again, this is not meant to be difficult. Usually the cases that you consider are like very simple individual decisions, like either I use it or I don't, right? So case 2 is optimal solution for J items does use item J. right? And now we just think about each of these cases, because the optimal solution is either, so the optimal solution is going to be the max of these two. Either I use it, and that's going to give me some value where like I for sure use the turtle, and that's going to give me like, you know, the maximum size, the most value I can get from a backpack with size X, given that I definitely use the turtle, is this. And this is going to give me another answer, which is going to be the maximum size of a backpack of size X, given that I did not use the turtle, is this. And our answer is going to be the maximum of the two, because I can use the turtle, but maybe I choose not to, right? So case one, if you don't use item J, capacity X, right? So we're not going to use the turtle. Then what is the smaller subproblem that we should already have an answer to here? So I am saying, so I'm talking about case one. So I'm saying K xj. In case one, what is this equal to? So if I know I will not use the jth item, then what is the maximum value that I can carry in a backpack of capacity X? Sorry, J minus 1. Yes. So this is just K of X, J minus 1. Right. And you're done. You made the problem smaller. That's all you have to do. You just have to make it smaller. So you made it one smaller. Ideally, you already know the answer to this because you solved it earlier. And then that gives you the answer to this. But that's not the only case, right? Oh, yeah, you guys, yeah, you did it. Great, good work. J minus 1 items, right? So that's what you guys said. The other case is I do use item J. So again, in this case, if I know that for sure I'm going to use the turtle, what is the maximum value of my backpack? So remember, the value of the turtle is given by V sub J. That tells me how much it's worth, like how many dollars. And W sub J tells me how much weight the turtle weighs. So in this case, I'm saying I know for sure I'm going to take the turtle in my backpack. So what is the maximum value I can get out of my backpack, given that I know it has a turtle in it? So at minimum, it has the turtle in it, right? So I must have at least the value of the turtle because it's inside, right? Plus, is there a smaller version of the problem that would give you the answer to what is the maximum value I can get?
Do you subtract the weight of the turtle from the capacity X?
Right. So one thing you would say is you would say, well, I now have less capacity, right? So for sure, it has to be at least this. And then what would I put here? J minus 1, because I've used the turtle, right? I can't use that anymore. So this tells me what is the most money I can get in my backpack, given that I can use everyone except the turtle, and I only have space. Like I'm leaving over space for the turtle, right? And then we add the actual value of the turtle because we're taking it. So this is case 2. Does that make sense to everyone? Those are the two cases. Not really? Some questions? If you've got questions, you should answer because these are, or you should ask because these are like, this is it. Like once you figure this out, then the rest, you're done basically. The rest is just writing for loops. Okay. Yeah, question?
What is the X minus WJ mean?
Yeah, so the X minus WJ saying for this problem, I have, my backpack can fit at most 10 pounds, right? For this part, I'm saying, well, I took the turtle, so I cannot fit. I have to take whatever the weight of the turtle was off from the 10 pounds. Oh, so the VJ is saying, once I know the answer to this optimal answer, I can add my value because I know I'm taking the turtle, right? This might be a little off. I'm actually trying to think if there's because I think there's like a max over something here that I'm missing. We'll try it. All right, so keep that. If you understand that, that's good. We'll see if I'm wrong. I'm trying to. This is hard, so I actually don't remember if I'm wrong. But I guess we'll see in the next slide if I did the wrong thing. Woo! No, yeah, but you guys are supposed to think about that. You kind of made through it. Yeah. So the optimal solution is j minus 1 items and a smaller knapsack, which is actually what we just talked about, which when you guys figured it out. So now we have identified the optimal substructure. We are very close to getting the recursive formulation, right? So it actually turns out that this is the recursive. So that's a little hard to read, but this is case 1, right, that you guys just talked about. So that's the one where I don't take item j. And this is case 2, which is I do take item j. And the answer to this problem is, well, whichever of these two is bigger, that's the answer. Because there's only 2 choices. Either you put the turtle in or you don't put it in. If you put it in, this is your answer. If you don't put it in, this is your answer. So the optimal one is the bigger of the 2, right? So again, if you got these 2, then you basically, you know, the next one, like you very often put a max of the options, right? And then we talked about these. You guys already told me kx0 is 0, k0j is 0. So we have our base cases, we have our recursive step, and we have our sub problems. So at this point, we're basically done. So again, if you guys are still, so who is having some trouble understanding this piece? All right, and in general, you guys should know, like dynamic programming is considered one of the hardest parts of this class. So if you're getting it, then good for you, because yeah, it's generally considered very hard. Yeah.
This problem makes sense, but I'm sure if we use like a different example.
Like a slightly different one, yeah. And the other thing is, like, you should keep in mind, like the problem with computer science, like a lot of difficulty in this problem is first finding what is the optimal substructure. Like I told you, have smaller backpacks, have less items, number the items from 1 to j, right? Like you might have thought like you have some set or something, right? Like that is just, you try it, to be honest with you. If you're seeing a brand new problem, you try it. The other thing is, like, once you see enough of these problems, usually there's some, you kind of see tricks that are like reused, and you're like, okay, maybe I'll try this trick, maybe I'll try this trick. Yeah.
Yeah, like I'm sure if you guys come up with this on like our own analytics, come up with.
Oh, well, your homework 7 has a problem where you have to come up with this. So hopefully you can do it. All right, so once we do step 1, identify optimal substructure. Step 2, we now have the recursive formulation and the base cases. Now step 3 is we use dynamic programming, which means we write the for loops, right? So here is the pseudo code. Okay, so again, in general, a lot of times dynamic programming algorithms are very easy to code, I'll say. We set up our base cases. So we're going to have a matrix K that is going to be a, you know, n by w matrix. That's going to have all the answers to sub problems. We're going to set it equal to 0 for all x0. We're going to set it equal to 0 for all 0i. And then from x equals 1 to w, and for j equals 1 to n, this is case 1. This is case 2. The only tricky part is you have to remember, you can only take case 2 if your item even fits in the backpack, right? So that's why you have the if statement here, which is if my item doesn't fit in the backpack, there is no case 2, right? If I got a backpack of size 5 and the item is a turtle that weighs 10 pounds, there is no, I take the turtle, right? You can't. So once these 2 for loops are finished, you return the answer. And we're going to walk through an example, but that's it. You guys solved it, right? What's the running time of this? Yeah. O of n squared. Okay, close. So this is O of n, and this is O of w. We're gonna say w because w could be very different from n, so we're just gonna keep it. But yeah, you're right. So of nw. So it's the same running time as the other problem solved. So surprisingly, it's a harder problem, but it has the same running time. Anyway, yeah, running time nw. And let's just walk through an example. So again, this is what your matrix would look like in code, right? So in C++, it would be a vector of vectors, right? In Python, it'll be a list of lists or something. You set it up, you fill in all the zeros. So you're filling in these rows, right? For j equals 0, you put in 0 everywhere. For x equals 0, you put in 0 everywhere. That's your base cases. Then you start with x equal 1, j equal 1. So what this is saying is I'm going to fill in the rows. I'm going to fill in the columns. Yes, I'm going to fill in the columns because the X is the outer loop. It actually doesn't matter which way you do it in, but the X is the outer loop, and I'm going to fill in the columns. So what goes here? So for j equal 1 and x equals 1, what are we considering? Huh? Yeah, so turtle is item 1. Okay, so we are considering the case where I have we're looking at whether I take the turtle or not. And we're looking, I have a backpack of size 1, right? So in this case, there are 2 options because the turtle only weighs 1. Either I take the turtle, so that's going to give me 1, value 1. That's going to give me this, right? It's going to be value 1 plus 1 minus 1 because the weight, I can no longer take, the turtle took up 1 weight. So this is 0, j minus 1, so that's 0. And that's actually, you already know the answer to that. It is this one. So that's going to be 0 plus 1, which is going to give us a 1 here. That's one case. The other case is I don't take the turtle, in which case I have a backpack of size of capacity 1 still, but now I can only take 0, like everything up to the 0th item. So you're actually going to be looking at this value. And from this one, you're going to get 1. From this one, you're going to get 0. You take the max and you put that as the answer, right? So yeah, we look at this one in the first case. Turns out we can take the turtle. 1 is bigger, so turns out we're taking the turtle. Then we fill in the next one, right? So now we're looking at the j equal 2 here. So now we're considering what do we do with the light bulb? Do we take it or do we not take it, right? And this is, again, so the light bulb now weighs 2 pounds, right? So we're considering the case where the capacity is 1. So we actually can't take the light bulb, which means the optimal solution is just take the turtle, right? And similarly, for the j equals 3 case, you're looking at the watermelon, but again, the watermelon does not fit in your backpack size 1, so the optimal solution is take the turtle, right? Who wants to get me started on x equals 2 for the first one? So now we have a backpack of size 2. I'm considering, do I take the turtle or not? Yeah.
Just before we're
Yeah.
trying to get the highest value. Right?
Yes, that's what we're taking the max. So we're always.
Not take the turtle, you take the light bulb. You would
Ah.
take all your,
Yeah, j equals 1. So you only have access to the turtle. Yeah. So right now you only take the turtle because you're not even thinking about the light bulb, right? Okay, so that's the maximum. Now you consider the light bulb. And this is the one where it gets interesting, right? It says, well, I could take the light bulb because it does fit in my backpack. Okay, that's this case. So if I take the light bulb, then I no longer have, now my backpack has used up 2 pounds of its weight. So I take the light bulb who has value 4. So that's, I get at least 4 in dollars plus K0 of the turtle of 1, right? And thankfully, we actually already answered that, which is here. Turns out the optimal, if you can only take turtles, but you have a backpack of size 0, is 0. So this is just 0 plus 4, which means you get value 4 if you take the light bulb. The other option is you don't take the light bulb. So if you don't take the light bulb, you just look, at kx. So you just go up the column, and you. So we're here. You go up, and you notice that, well, the maximum I could possibly get is 1. So I take the turtle, right? So the max of 1 and 4 is 4. So it turns out here you take the light bulb, right? And then you keep going, right? So who wants to do the last one in this column? So now I'm looking at j equals 3. I'm considering the watermelon. Yeah.
you still take the light bulb.
Yeah, watermelon doesn't fit. I still take the light bulb, right? Okay. This one turns out you still just take the turtle. This one gets a little bit less interesting. Turns out more interesting. Turns out you take the turtle and the light bulb. Okay. And then the last one, it actually turns out you just take the watermelon, I think. Yeah, for 6. And you can see that, like, as you're filling this in, you have the answers to the smaller problems. So that's why dynamic programming works. So in a sense, dynamic programming is like this idea of, like, you have one problem you're trying to solve. So what you do is you break it up into many, 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 many small problems. And then you solve the small problems in a certain order such that you will be able to use them to build up your bigger answers. Okay, great. Step 4 is you maybe add some extra information to your pseudocode to actually keep track of which items you're picking. So you guys do this one, I guess. And then step 5 is you actually code it up. So you guys are going to do this on the homework. So you guys do that. So again, what we have learned, we can solve the 0-1 knapsack in NW time. And again, we just went through our recipe, right? So at the end, we kept a 2-dimensional table. We created smaller items. Everybody got that problem? If you guys look at the previous lecture, the problem was very similar. If you look at the least common subsequence, the problem was very similar. So again, this is why we call this dynamic programming. They're all using the same strategy. Okay. And then, yeah, this is a question you should ask yourself, which is like, how did we know what is the substructure to use? The answer is, I told you, right? Like this one made sense. It ended up working out. The answer in real life is you try some stuff and you see what works. That's the best I got for you. Okay. If you're really smart, maybe you try some really good stuff and you get it like the first time. But I think in general, it's just like, if you think you have a dynamic programming problem, you try to break it up into smaller problems. You try to do the process of like writing the pseudocode. And at some point you're like, oh, this actually doesn't help me solve the bigger problem. Or you're like, it's going to take a lot of work to solve the bigger problem. So this is not a good sub problem. Let me try a different one. All right. And that's why dynamic programming is hard. So we have 10 minutes. We're going to do, who wants to do another dynamic programming problem? Okay, cool. So we're going to try to get through this one. One more, guys. So this is called an independent set problem. So this is a little bit more theoretical. I don't have a lot of like real world applications of this problem that I've personally seen. I'm sure it's useful somewhere, but this is a little bit more theoretical. We're going back to graphs. So this problem says, given a graph with some vertices where each vertex has a weight, right? So now we're going to say we have a weighted graph where the weights are on the vertices, not the edges. Okay. So now each vertex has a weight. So this one's weight 1, this one's weight 1, this is 3, this is 5. Okay. The question is, what is the independent set with the largest weight? So again, it's an optimization problem because you're looking for the largest, the maximum. And then an independent set is a set of, so it's a collection of nodes that do not share edges. Okay. So it's a collection of nodes that are not connected. That's an independent set. Okay. So for example, 1, 1, 2 are independent because there's no edge between this one. There's no edge between them. 1, 1, 2. These 3 have no edge between them. 1, if you take 1, you cannot take 3 because there's an edge between 3. If you take 1, you cannot take 2 because there's an edge between them. So independent set is if I look at the nodes I took, there's no edge between them. Okay. Does that make that's the problem? All right. So the problem is for all possible independent sets that you could think of, what is the one that has the most weight? So I guess a real world application would be, I guess it's similar to the fish and tank thing or something. Maybe your fishes are like worth money, right? Or something. And you're trying to figure out what are the fishes I can take that are worth a certain amount of money. But I don't want to take any fishes that fight with each other. So there's no edge between them, right? That would then that problem becomes this problem, the maximal independent set. Okay. So surprisingly, again, this is why computer science is pretty hard, which is it turns out this problem is what we call NP hard, which we're going to cover at the end of class, which means there is no known polynomial time solution for this problem. Okay. The best solutions we have is try out every possible single subset. Yeah.
So when you're trying to find the largest weight, are you just basically adding the weights of things that don't have connections to try and find the largest one, or is it...
Yeah. So the idea is like so one reason this is hard. So like you might say like, well, I'll definitely take the 5, right? Or something, because it has a big weight. But the reason this is hard is that when you take the 5, you can no longer take the 2, you can no longer take the 3 because they're connected. So you don't know if you should have the 5. Maybe it's better to have the 3 and the 2 and not the 5, right? like, for example, if this was a 3 and this is a 3, then if I take these two, that gives me weight 6. But if I take just the 5, it gives me weight 5. But maybe this 2, if I take it, it excludes this guy and it excludes this guy too. And maybe this guy has weight 10. So maybe really I should take the 5 so then I can take this 10, right? So that's the best solution we have for this problem is try out all possible ways of taking the nodes that are not connected and then measure how much they weigh. Yeah. Oh, for this one? That's good. I actually have no idea what it is, but what is it actually? 9, which is what? It's the.
Take the 5, you take the top 2. So if you take the top 2, you can take both of the ones on the outside.
Sounds reasonable to me. Sure, that might be it. And now the question would be, can you, whatever process you used in your head, can you come up with an algorithm? And what I'll tell you is that people have been trying to do this since the 1970s, and nobody has come up with an algorithm for the general case that is not try out every single one and then see. Okay, just FYI. So that's the problem. So already, like, if you guys figure this out, like, hit me up. We can write a paper. We'll go straight into the Hall of Fame for computer science. So like, please try it, figure it out, but just hit me up beforehand so that I can take all the credit. No, I'm kidding. You'll be on the paper, okay? Yeah, don't worry. Yeah, so it turns out that, like I said, this problem is actually something that we call NP complete, which means there's no polynomial time solution for it. And it's even stronger than that, which says if you found a way to do this with polynomial time, you would essentially break the entire internet. So I know I've brought this up a lot of times. I will cover it in more detail at some point because it's really cool. But if you are able to solve these problems that I'm telling you are NP complete, if you can do it, then like a lot of our cryptography is broken. Okay, it relies on the fact that these problems don't have a fast solution. Okay, which gives us a lot of confidence to say there probably isn't a fast solution. But again, nobody has proven there's not, but a lot of people have tried and nobody has found one. Okay, so instead, what we're going to solve is we're going to solve the maximal independent set where we assume that the graph is a tree. So that problem has a solution, has a fast solution. Why? Because we are assuming that it is now a tree. Okay, in the general case, there is no good solution, but if you assume it's a tree, then a tree is a connected graph with no cycles. It has a root, right? It has children. So if you assume the graph is a tree, it gives you a lot of structure, which then you can use to solve this problem quickly. Okay, so that is our new problem. For this one, it turns out this is the maximal independent set. This is a tree, by the way. I know I didn't draw it as a tree, but this is a tree. You can imagine you can pick it up from the 5 and then you have children, or you can pick it up from the 3. You can pick it up from anywhere. It's a tree. Stuff like that. Cool. So again, step 1 is identify optimal substructure. So anytime you see a tree, your immediate thing should be optimal substructure are subtrees. Okay, that's like a pretty standard trick out of the book. So subtrees are a natural candidate. So you can imagine that there are 2 cases for the substructure of the subtrees. Either the root of my tree is in the set. So either I take it as part of my independent set, which means what? If I take the root, what does that mean about the tree? I cannot take the children, right? So either I take the root or, oh, I guess I did it backwards. Either I take the root or I don't take the root. Okay, those are the 2 options again. And this only works for trees. If you try it in a general graph, it won't work because you have cycles. Okay. So let's talk about case 1. So let's say the root is not, so I don't take it in my maximal set. Then what does my answer look like? What are my, I guess I didn't give you the actual sub problems. Or we can just talk about it. So if I don't take, if I know my root is not going to be in the maximal set, then what is the weight of the maximal set of this tree, of the whole tree? Where the sub problems are the subtrees. Yeah. Yeah, so there are two, we talked about it, there's two cases. Either this root is going to be in my set or it's not. Okay. If it is, then I cannot take the children because there's an edge, right? But we're talking about just the case where I know I won't take it. So I know this will not be in my maximal subset, right? I'm assuming it won't be. Then what is the answer for the maximal subset problem? Using like smaller subproblems. Yes, Serena?
So it's either the greatest independent set from the left subtree or the right subtree, like the maximum, comparing those two subtrees.
Close. Yeah. Yes. So this tree is actually independent of this one. So you can actually, you don't take the max, you take the sum of the two. Yeah. But that is the optimal. If you knew the maximal independent set for this tree and the maximal independent set for this tree, and you know you're not taking the root, then the answer is just these two together. Because there's no edges, because they're trees, you know there's no edges between them, right? Cool. So let's say the root is in the maximal independent set. Then what is my answer? So I know I'm definitely going to take the root. Then, like we said, we know we cannot take the children. So yeah. Yeah. So again, you look, if you knew the answers to the grandchildren, then the end, if you're taking the root, the answer is going to be the weight of the root plus the maximal weight here, the maximal weight here, the maximal weight here, the maximal weight here, right? But you cannot take the children, right? So that is our optimal substructure. Again, so if you see trees, optimal substructure, usually the subtrees, right? And then you can write the recursive formulation, which ends up being this. So let AU be the weight of the maximal independent set with root U. Okay, so with some root of my node, then the weight is going to be equal to the maximum of two cases. Either this first case is I do not take the root, right? The second case is I do take the root. All right, we're at 12:50. I will wrap it up next time. It turns out that this formulation does not work. Okay, so think about why. It kind of works, but it's too expensive. Let's say that. So this does not work, but we will tweak it and we'll wrap it up on Friday. Thank you guys. I hope you guys are, I don't know, dynamic programming is really cool. I really like it. It is my favorite subject in the class, I think. Actually, no, I think the NP completeness is very close contender, but I definitely like it more than hashing, I'll say. Anyway, thanks for coming and thanks everyone on Zoom. I will see you guys on Friday.